frequency domain analysis. So we'll try to get more insights, and I'm also going to show you analysis on the exact same data set, right? And that will also boost up your confidence about how to go about such analysis, right? I did not ask you to write any code from scratch for the homework. You are just going to use the Python API, numpy.fft, or like SciPy, I think also has a DFT. So you're just required to do that. But we are now going to look at the internal mechanics of how this thing actually works, so that you have more intuition about applications that you might find this kind of tool useful, right? So the entire class is dedicated for exploring sensing techniques, and this is one of the cornerstone technique that you have to, like, this is often useful for many types of analysis, starting from IMU data, inertial motion sensors, right? We use those accelerometer, gyroscope, and the activity recognition, gesture recognition, and even for very simple applications like this heart rate detection using the IR sensor that we have already encountered, and also as a part of the PPG thing that you are doing using the camera output of your blood flow video, right? For all this periodic phenomenon, we do have to look at this frequency domain tools, which kind of gives you a black box to look at frequency domain components at the get-go, whereas time domain data, where you are evaluating the time series, sometimes becomes a little bit more stressful, right? You have to basically remove the noise on your own, look at how the peaks behave, and also you can do a first cut analysis using the frequency domain tools. So I'll just try to recap whatever we looked at in the last class. We were talking about this imaginary tape that had this repeating numbers, right? The repeating colors, starting from the red one, and which gets repeated at every 5 gaps, and then we had this green color that was being repeated at every 8 gaps, and so on, right? And we also saw that how could you fold this tape or cut this tape and stack them on top of each other, which can bring out this nice pattern, right? For example, when we cut the tape in blocks of 5, right, in chunks of 5 intervals or 5 gaps, and stack them up nicely, we could find out the red color, which was nicely stacked up. And if we look at every column, we could see that compared to other members in this group, other colors in this group, the prominently the red color shows up. Right, same is the case for other kinds of offsets that we were using. So this is, let me call this as an offset, right? So we started with this intuition and did an analog in the domain of colors, right? And where we had repeating colors, and we tried to find out a systematic way, right? It's a kind of an algorithm in which you can actually find out the frequency of the repeating components, right? The repeating colors. So how often were they repeated? So, and we try to draw an analogy in this color context, as I told you, and we wanted to apply the same concept in case of repeating patterns of amplitudes. Wherever you might be getting some sensor data which have some kind of repetitions that could be encoded inside it, that is not apparent from just by visual inspection, but there could be certain amplitudes that could be repeating at a certain interval of time, right? And rest could be like lots of non-repeating things, right? But finding that out, right, just by doing an analysis in of this time series, for example, which I have shown here, it's very difficult to figure out that how many how do you want to segregate this data into different independent repeating patterns, right? For that, we have to figure out a way so that we can chunk out the entire data set into multiple distinct data sets for each and every frequency. Okay, so what does this frequency mean? Frequency is basically how often a certain amplitude is repeated. Okay, so if you break it down, you basically get all these things that I have shown, right? It could be a frequency of f1, right? There is some thing that is happening at a that is being repeated f times a second, right, which is f1 times a second, and there could be f2 and there could be, let's say, f3, right? And then what you see is a combination of all these events together, right? This could be let's say a temperature data you are reading from a sensor, and but the sensor is actually going through certain location, like it's actually a mobile sensor, right? And it is encountering different types of objects at periodic intervals, right? Let's say this is a factory sensor that is installed on a robot, and the robot moves around, right? And basically what you are reading is the temperature data from the sensor, right? Because the robot is moving, it is visiting certain like high temperature zones, let's say, at a certain period, right? And that period somehow reflects in your temperature data that you are reading from the sensor. Now, if you sit down with that data and try to do this such analysis, how wherever you segregate different independent frequencies out, from there you can figure out such, you can derive or infer such things, right? If you knew the context that the sensor is installed on a robot, and you can make some inferences about the robot's movement, right? How often it visited certain areas which is of a certain temperature, and so on. Okay, so that is our interest, right? And I'm basically taking you through the mechanics of how this thing works. And after that, we also spoke about the coiling machine analogy, where we were taking this time domain data, which is basically linear in the linear form, where x-axis is your time and y-axis is the amplitude, right? And what we were trying to do is taking this particular time series, or taking this vector, right? It's a chunk of data that is sorted in time, and wrapping it around this imaginary circle, right? And how are you trying to wrap this? This is wrapping it at a certain frequency, or we are trying to restrict how many times we are wrapping it around the circle. So that is important, right? And you can, for this analogy, you can assume that this is sort of an like very elastic sort of a tape. Okay, so if you are talking in terms of samples, that is not a problem. You can always make a sample spawn a certain angle, right? That is always possible. And as I told you in the last class, for a certain value of f, where f denotes how many times you are wrapping it around the circle, there could be certain values of f where some of the data set of your interest stacks up nicely, right? They are all coinciding for a certain value of f. Okay, so we are trying to look into such patterns, right? We, in the last example where we were showing an analogy with the colors, you could also see that the green color or the yellow color were stacked up nicely. In that case, we were cutting out the tape and stacking them on top of each other. In this case, we are sort of doing the same operation. Instead of folding it like with cutting it with a scissor and stacking them up, we are folding it in this imaginary circle, right? And what we were interested in is quantifying some kind of a metric to make this odd man out, right? So this is f1, f2, f3, and f4. Out of this one, this showed prominence, right? Let's say prominence in the final, let's say, metric. I won't name it anything by any specific term right now. Let's say we want to get some kind of a metric, which I call on the right hand side a resultant, or like a center of mass. Could be a close approximation to what we are aiming at, and this could assign some kind of a weight to f4, right? So, or the metric that we are talking about. So in the last class, we wanted to assign some wi to every fi, right? So wi is some kind of a metric or some kind of a weight that could be assigned to a certain frequency component, right? So f1, f2, f3, f4 are the different tries that we have made. So f1 could be like, let's say, 5 rotations we made around the imaginary circle. f4 could be 10 rotations, and so on. Okay, so in terms of signal, on the left hand side, this is our input signal, and this is being input to the coiling machine. And to the coiling machine, we ask this question that whether F1 is present, whether F2 is present, dot dot up to Fn. Right? We ask a series of questions, and for every answer or every weight, right, it could either return yes or no, or it could return some weight Wi, which is going to tell us that which of the Fi's are dominant. Right? Out of this F1 to Fn, you might happen to see only 5 or 6 prominent peaks, right, where rest of them do not have a very high weight that is assigned by the coiling machine. So the output of the coiling machine again would be this mapping from Fi to Wi. Okay. So was this this slide that was going on, or the last slide?
No, sir. Last 20 to 30 seconds only we missed you, sir.
Okay.
Yeah.
So this was clear, right?
No, up to this it is okay, sir. Wait to the
yeah. So for this slide, this is a repetition of the same slide that we had in the last class.
Yes,
so this is just trying to formalize the technique that we are going to see right now. So on the left hand side, we have this input signal, which is a time versus amplitude relation, and this is being input to the, this is an input to the coiling machine, which is going to output this weight, right, for every given frequency that is being queried upon. Right? If we query it with some frequency Fi, it is going to tell me what is the weight that could be assigned to Fi, right? So that is Wi. And depending on the relation between all these Fi's and Wi's, we could figure out out of a set of Fi's, which of the Fi are more prominent than the others, right? So in this mix, right, I would call this is a mix of different patterns, and out of this different patterns, which of the patterns are more prominent, right? It's not that it is going to have all the patterns starting from F1 to Fn. By pattern, we mean some sort of a repeating event and repeating at a certain frequency. Okay, and the task of this black box or this machine is to give me this data set, right? The mapping from Fi to Wi. Okay, so hope this is clear. Okay, so now we are going to move forward and look at how we can go about implementing this idea, right? So we will start with, let's say we have n samples. These are just sensor data that you are receiving, and n of them are there. You could have 100 data points, you could have 10,000 data points, you could have 500 data points, doesn't matter, right? And our task is to feed this data to this system. Okay, so our task is to take this data set and feed this data. And of course, this data set, this is a sorted list that you have to sort it in terms of time. So this is ordered, right? You cannot really mix these n samples, right? They are not independent given the time axis, right? So they are all ordered in a certain way, and you have to basically give this vector or this ordered list to the coiling machine, and that is going to figure out what are the dominant F's that could be present in this sample. Okay, in this data set, let's say. And for our purpose, we will start with something simpler, right? Instead of looking at n samples, we will assume that n samples taken at a rate of k samples per second. Okay, which is very important here. N is the total number of samples, fine, but the total number of samples n could be collected over a period of 1 second, or it could be collected over a period of 1 hour, right? There is a lot of difference. So when somebody gives you the data set, you also have to know the timestamp values of all the samples. You have to know at what point in time a particular sample was collected. Okay, so what is the thing that we are going to look at right now is we are going to base the discussion on a particular chunk of 1 second. So S is basically a second. So this is second 1, second 2, second 3 up to the 6th second. This is the 6th second. But what is common to all these seconds is that in every second you have k data points that were collected. And this is important. It was collected next second. Although this might happen in a practical situation, but for now we are trying to make the model as simple as possible so that you get the crux of the idea, and then you can always make some variations and see for yourself that how the system responds when you have slightly non-uniformity, right? Slight non-uniformity in your sampling rate, right? Which is often common in real sensors, right? When you extract data out of it. Okay, so what we are going to deal with is, as I told you, we are going to deal with this chunk of 1 second, and then that is the entire data set that has to be fed to our system. Okay, so our total time in the linear domain is k samples worth of data, which is basically 1 second, and it has to map to the circle. We are wanting to map this thing to the angular domain, right? So we have to find out the total angle that will be wrapped by this k samples. Okay, so we are taking this chunk. Let me restate what we are trying to do. We are taking this chunk of 1 second which has k samples, and we want to convert we want to wrap this particular string or a tape, imaginary tape, across the circle, imaginary circle again. How many times? F times, let's say. Okay, we are going to take it and wrap it around f times. Okay, so what will be the total angle that will be wrapped? What will this thing map to? We are trying to find out. Yeah,
2 pi f radian.
Yeah, exactly, right? So 2 pi into f. So f rotations, right? F rotations we are making. So 2 pi into f will be the total value of the angle that will be spawned by the k samples. So 1 second will map to 2 pi f radians in the circular domain. Okay. Now, in 1 second, since we are taking k samples, wrapped it around f times 2 pi f radians, fine. So what will be the per sample angle wrapped? Because in the last slide we were wrapping it, right? So basically sample 1, sample 2, sample 3, sample 4, sample 5, sample 6, and so on, right? Like this. Let's say this is completion of one rotation. Now there will be more samples, right? Now second rotation is started. So if you see, every sample is going to spawn some angle, right, in the circular domain. Okay, in the linear domain, the sample will spawn some time, right? Why? Because every sample is being picked up after a certain interval of time, right? In 1 second, you have k samples that has been picked up, right? So this is 0 seconds start, and this is 1 second, right? Within this 1 second, you have k samples. So there is some interspacing in between the samples, right? This is sample I and sample I plus 1. There will be some interspacing, and that interspacing will be directly dependent on k, right? There are k samples, k spacings in this 1 second interval. Similarly, in the 2 pi f case also, we are spawning the total angle of 2 pi f radians and dividing it into k samples, right? So the per sample angle that will be wrapped will be 2 pi f divided by k. Okay, so if we are talking about the nth sample, right? So we are basically taking one sample out of the linear time, the time series that we have, and our task is to put it on top of the circular system, right? So let's say if we start this as like a 0 degree or 0 radian, let's say I could have put it on the positive x-axis side, but it doesn't matter. We'll just follow the convention here, whatever I have drawn, and then we want to offset it by a certain angle, right? And what will be the value of this angle? So what will be the value of phi n here? Let's say we are just skipping some samples, right? We are skipping n minus 1 samples, and then we are now on the nth sample. We have to make some movement, right? From 0 radians, we have to go a certain distance, and certain distance in terms of the angle, right? What will be the angle that will be offset for a particular guy of this particular sample, nth sample? So we are basically mapping. No, we are just mapping this. This is the linear time domain. So this is time, right? This is the frequency of the circular domain. This is the angle. So I just want to know from some of you that what is the value of phi n?
2 pi fn by k.
Exactly, right? So try to respond, right? These are simple things. I'm trying to ask all these questions so that I have a feedback from you guys, right? Because like in an offline class, I could see your face, I could interact with you. Here it becomes sort of a little bit problem from my part, right? Because I don't know what exactly is getting through, right? So 2 pi f by k is for one sample, and then multiplied by n, right? So that gives you a clear cut idea about how much you want to shift a particular sample in the circular domain or in the frequency domain. What will be the angle that is formed? Okay, and note that it is going to come back like 2 pi f could be a very large number, right? It is 2 pi f by divided by k. It can go around the circle multiple number of times, even that is possible, right? It can go about 5 times and then come back here. So this is not always going to be something like this acute angle that I have drawn, right? This phi n value could be very large. Okay, because we are talking about f rotations, right? F could be itself, let's say 5 or 10 or 15 or 20, right? Even kilohertz, right? It could go to 20,000 times per second. Okay, so this is just for a visual clarity. I have drawn it like this. Okay, so now I give you a real example. Let's say this is not a real signal, this is a synthetic signal, and we are going to deal with this synthetic signal for the time being. And this is a sine wave, very humble sine wave, and we have a duration of 1 second. And what is the sample rate of this particular signal? How many samples per second have we collected?
5.
No, samples per second.
Okay, 20,000 samples per second.
We have 20,000 samples, right? So yeah, so this is just a very dense plot. That's why you are not able to.
Sir.
Yeah, sorry, yeah, 2000, whatever, yeah. So 2000 samples we have collected. This corresponds to 2000, right? And this was collected in the span of 1 second, right? So this could be a sensor data, whatever. So it is collected 2 kilo samples per second, and we want to wrap this. This is wrapped, right? This is actually wrapped. So in the polar domain or the circular domain. So I have marked the starting point here. So this is your starting point. I have also marked the starting point here, right? And the starting point and the ending point will coincide. And this, I have marked all these peaks, right? And somebody mentioned 5, right? So 5 is here the number of repetitions you had, like the frequency is 5, right? You had like 5 complete cycles. Okay, and you can simply mark the peaks, right? As just to map it from the linear domain to the circular domain for those who are still not able to understand. So A maps to this part A, and I also have color coded it, right? For your simplicity, I could have shown a simple color, but single color. But yeah, I have actually used a gradient so that you understand the different portions of the time domain signal being mapped to different angles. So B gets mapped to B, right? You can follow this particular thing, right? At 90 degrees. C gets mapped to C, D gets mapped to D, and E gets mapped to E, right? And then if this is F, right? So this is the portion is F, right? That comes back to 2 pi. And I have made 1 hertz, right? So the rotation speed is 1 rotation was done across the circle with a data that is worth of 1 second. So for now, we will just restrict ourselves to 1 second worth of data only. Later, we will see that how to deal with sample rate and so on. But currently, we are just sticking to the fact that all the input data we have is in terms of 1 second. Okay, and this has k number of samples, so k is your sample rate. So we wrap it around the entire circle, and I guess there is no confusion among you guys that how this wrapping is done, right? These are all samples, right? We have just picked up samples, so the samples are very densely placed in this particular example. That's why you are not able to see these gaps, right? So I've chosen this the 2000 value purposefully, so that you don't see like something like an empty plot, right? But there are actually small gaps in between them, right, which you cannot see. Okay. So how many samples can I ask you spawns from 0 to 90 degree? So if I want to say that from 0 to 90 degree, right, how many samples are there? How is this particular portion of this picture maps to the time domain? How many number of samples? 1000 samples, 1500 samples? How many samples are there?
500.
500.
Yeah. Yes. Right. So 500 samples gets mapped. So now we have seen for a long period of time that how this 1 Hz case gets through. Okay. So we are not still working with the resultant part that we were talking about. We will come to that later. Okay. So if we look at this case with this 2 Hz, what will happen? So we'll first take this 0 to 2 pi, map it, right? So we are not going to cover this entire signal in the first rotation. So in the rotation number 1, which is I call the first loop, we start from this black part and this end up here, right? Which is the brown kind of part right here. Okay. So this makes the first loop complete, and this will be mapped from 0 to 2 pi that I have shown. Next one is the remaining part of the plot, right? The remaining part of the signal from the 1001th sample to the 2000 sample. Till this, we are going to put again, we are going to start the next rotation from this point. This goes all the way till here, till here, till here, and then finally it comes to this yellow part, right? And what will happen if we superimpose these two? Because what we will get is a superimposition of the first loop and the second loop. This is a continuous process. I broke it down for you to understand, right? What will happen from 0 to pi, the first loop, 2 pi to 4 pi, that is the second loop, right? If the third loop could be present. So if you do a superimposition of these two pictures, right, these two loops, what you will get at a rotation speed of 2 Hz is a picture like this, right? So the layout of the different samples in the frequency or in the angular domain will be this. Right? So these are all samples that are present. So this is a way of orchestrating or organizing the sample in a different way, right? Earlier we were sorting it just based on time. We are now somehow arranging them in terms of angle. Okay, that repeats, of course, from 0 to 2 pi, after that 2 pi to 4 pi, and so on, right? Because we can only go from 0 to 2 pi. Okay, I'll give you a third example so that this really gets onto your head. So if we work with a 3 Hz coiling machine, so we'll basically do 3 loops, right? The first loop will be from 0 to 2000 divided by 3, right? And this is mapped as you can see in the picture. So this is pretty much the black part of the signal. Then comes the brown part of the signal, which is again starting from here, right? Goes all the way, again spawns 360 degrees and comes back to 2 pi, right? But it's actually 4 pi because you have already covered from 0 to 2 pi here. Now in the second rotation, you are basically doing from 2 pi to 4 pi. Okay. And what will happen in case of the third rotation? The yellow part is 4 pi to 6 pi. So you are taking this stretch, right? You are basically taking this imaginary tape on the left hand side and rotating it around. And for every rotation, I show you a snapshot what is happening. And after you superimpose this, you are going to get this layout for the entire data set, right? Or this entire ordered time series data. Okay. So this is your superimposed version. And I have given 2 more examples, or rather 3 more examples. One is with 4 Hz. Where you are chunking it in terms of 500 samples per rotation, right? So for 0 to 500, you do the first one, then the second one, third one, and fourth one. And on the left hand side, I've also shown the superimposed value, right? Superimposed distribution of samples in terms of angle. Okay. Now, what is interesting is the 5 Hz rotation. right? Because we already know that the rotation, the frequency that is actually present here is exactly 5 hertz. Although it's a synthetic example, it's not any real data set, but it is actually the rotation we have shown here is exactly one cycle of the sine wave that gets completed for every loop that we are making, right? This is the first loop, and we start from 0, right, and then again get completed to this is 2 pi, right, and which is actually taking out a complete part of the cycle, right? And then there are 5 cycles. For every cycle, it looks exactly symmetric, and this should register in your mind that why this particular technique is extracting this 5 hertz magically, right? If you look at this superimposed signal, if you look at, let's say, what was our so-called metric called center of mass, that will be somewhat tending to the one particular side of your this plot, right? Whereas in case of all others, it is pretty symmetric, right? Uh, it could be random also, but again, it's not something which is biased towards a certain direction. Okay, in all the cases, 3 hertz, 4 hertz, and in case of 5 hertz, magically you see this guy which is sort of odd man out, right? And we are going to quantify that pretty soon, but my idea is to get you through the intuition first, right? So that I could have bombarded you with a DFT formula, but I'm like deliberately not doing that because right, you will anyway encounter those things in your classes, like other classes, right? Where in here you need to understand the crux of the mechanics of how this thing started anyway, right? What is special about this particular operation which extracts this frequency domain components, right? And if you understand this, it is much more easy for you to develop algorithms on your own which involve such concepts. Okay, so I guess you could clearly see the difference in between this particular case as opposed to 1 hertz, 2 hertz, 3 hertz, 4 hertz, as well as like in this case 6 hertz, right? Whenever I'm making it 6 hertz and not 5 hertz, you see the entire thing changed, right? This is your superimposed output or the superimposed signal. Okay, so all of these are like bits and pieces of the entire time domain signal, and 6 hertz means we are assuming that there had been 6 repetitions, so we are trying to coil it around for 6 times. Okay, any questions still here about how the wrapping is taking place, or any observations that you want to say that I have not covered? Okay, so I hope that you have found out right through this series of examples. Yeah, any? Hello?
Yeah, no questions, sir. Sorry.
Okay, yeah, just keep it on mute. Okay, so through this series of examples, at least you have figured out that there is a clear-cut way, right? Or we are approaching towards a systematic algorithm which can actually help you figure out the frequency domain component that is present in this data set or this time series. Okay? And I'll show you what I call is running a search, right? Because this is something like a search operation that we have done. Every time we go to our Genie, right, the black box or the coiling machine, and ask it, right, whether a certain frequency, whether you are present or not, and it gives me a weight, right? So we have not yet gone to the weight, but at least we were seeing some kind of a pattern that was evolving from the system, right? And I want to do a more granular search, right? Instead of running it for every integer value, I did actually program it for any even fractional values, right? Because you can always make a fractional rotation. You can make like 2.5 rotations, right? That is perfectly possible, right? And what I'm going to show you is a output of that operation, right? So if you see on the top, I'm showing the coiling frequency, and for integer values, I'm showing how the plot actually looked like. So this is continuous, so that you can appreciate this entire evolution more. Okay, it's the same time domain signal, just that I'm showing you through all possible values, right? Basically sweeping the search space. In 5, it becomes very well behaved. Now again, it starts spreading around. Okay, so yeah, so this is basically, I show you all the snapshots, right, that I was this is a superimposed snapshot, right, of this entire this rotational phenomenon that we are doing with the coiling machine. Okay, hope this is clear. Till now, we have not figured out any weight, but at least we did run the search, and visually you could understand how these things evolved. Right, so we actually started from, like, say 0.1 and goes till 0. That is exactly what we have shown you in the picture earlier. Now, right, we go to, we just increase the value, go come to 2, right? So this is another sort of possible frequency which could have been there, but it's not there, right? And then let's say how it nicely stacks up, right? This is 5, so there is some relation with this 2.5 and 5, so it's like kind of partially stacked up on both sides, which is again going to cancel with each other, right? When we find out the center of mass, again it gets separated out, and with 3 and 4 it kind of fine, and then when it goes to 4.5, it's going to be in the vicinity of 5, it starts slowly lining up, right? And at 5 it is perfectly lined up. Okay, and again it starts to separate out. So this is the thing that I wanted to show you, and that's the code, that is the reason I have written this thing, so that you could, like, really appreciate what is going on in a continuous manner. Okay, okay, so we do something like a search, right? We are going to come back to all these things later. And now our next task is to assign some kind of a weight, right, that we have been talking from the very beginning, right? Because this visual representation is not something we would be able to work with, right? We have to figure out some kind of a metric that we can quantify and assign these things to every value of f. Okay, so when you say f is 2.5 or f is 3.7, we want to come up with the w of f. Okay, now let's see what is a good way to proceed. Okay, so now in this case, as we say that for any complex number, notation could be used when we are basically trying to use this two-dimensional data here. In this case, we have this amplitude and the phase. So in the Euclidean coordinate space, we can say ax is equal to the amplitude an cosine of phi n. So ax cos phi, and y axis we can say this is like an sine phi. Right? So this is the coordinate of a particular sample in this system. Right? If you look at the Euclidean distance x and y in this Cartesian coordinate space, and in the complex notation system, right? In the complex notation, we can also write it as an is the amplitude and cos of phi n plus j or I, right? It's a convention that we use j in this E discipline, whereas in mathematics they will use I, where I dot I is basically -1, right? And the complex square root of unity of -1, and so this j multiplied by sine phi n, right, which could be written in this Eulerian notation as e to the power j into phi n, right? This is very well known equation, right, to replace this cos theta plus j sine theta as e to the power I into theta. Okay, so this j is basically the complex square root of unity, wherever we use commonly you have seen I, but just for in this context, J could also be used. So this denotes a 90-degree rotation, right? So in our term, we are denoting, if we are multiplying it by I or J, this just means a 90-degree rotation. And if you are used to this I square is equal to -1, which actually means a 180-degree rotation, right? So if it was something like this direction, and if you multiply it by I square, what this actually means is that it reverses the direction, right? That's why you say that I square is equal to -1, right? If you just multiply it with I, it is just means it, instead of having a rotation of pi, you are having a rotation of pi by 2. That's all, right? In our case, we don't need to go into any further details of this. Okay, so and I think you are all well aware of the Euclidean, the Eulerian notation also. Okay, so you can also do it for one more signal. Sorry, one more sample. So that will have an amplitude of A2, and let's say your phase is phi 2, and all we have to do is, for many samples like this, because in the system you will have n samples, right? And for all these n samples, you have to figure out what is the sort of the resultant, or what is the center of mass of this entire data points that is lying in this r comma theta or r comma phi system, okay, in the polar system. Okay, so let's say this is another instantiation of the same sort of data that I was showing you. So let's say this is a continuous signal here, and since we have sampled the signal, so we will be picking up discrete chunks from this particular signal. Okay, let's say this is your signal that is wrapped around, right? So this is your coiling machine, and what we are going to do is we are going to pick up samples, right? So this is the first sample we have picked up, and this sample will have a certain value of an and phi, right? And so this is like a0 and phi 0, right? So this could be mapped as like a0 into e to the power j phi 0. Right? In the complex notation, we can write something like this. Okay, so same is going to hold for other things, right? There will be second sample, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, let's say, right? And this could go on, right? Because I just did to a finite extent, but if it is a sample that will be wrapped around for multiple number of times and so on, so this will go on. And for every such thing that you have already seen with so many examples that I have given, that every sample is going to get assigned some angle, right? Some phi, right? That 2 pi f by k into n or something that we have already seen last few slides back, right? And an is the value or the amplitude of that particular signal. Okay, so what we are going to do now, we are going to look at the average weight or the average value or the average position of all these data points, right? What will be this? What will be that? This will be simply 1 by n, and summation of n is equal to 1. There are 1 to n. There are n samples, and then summing it over this entire value, right? Which is for a particular sample, and doing it for all the n samples and taking an average. Okay, which could be expanded because phi n is something that we have already discussed. This is 2 pi f divided by n multiplied by n, a small n. Okay, any confusion till here? We are just trying to, we have already seen the intuition, right? We are just now trying to quantify that. Okay, okay, so I'll proceed. Okay, so now what I have just rewritten the formula, right? So in many classes you will just see that you will start a DFT formula with this, but now at least you have a decent background on how we arrived, right? So you'll see some approximation of this formula, right? It might not be exactly the same thing, but yeah, there are some notations that has to be followed with the sign and so on. But you have a pretty good idea about how we appeared or how we, what is the intuition behind it. Okay, so now like we have the black box sort of ready, whatever we call as the coiling machine or the frequency extractor. On the left hand side, the input is the time domain samples. We have n samples, 0 to xn minus 1. And on the right hand side, we have this n wets, right? Those are the n frequencies. Okay, n frequency components. And for those n frequency components, we are giving or assigning some kind of a weight. Okay, and how is this weight coming? The weight is coming just by the simple formula that we have stated on the top. Okay, and how are we getting into it? All this coiling machine funda we have just shown using so much animation and so on. So that is how, that is why basically such a technique is used. Okay, you have just seen it for yourself, right? How it is able to nicely, magically extract out frequency components. Okay, so this will give you enough idea about the prominence of the different frequency components. Let's say in this case fk, right? And this is not necessarily k hertz, right? We have to see that it could be mapped to a certain value, right? Which is k hertz if your your time is 1 second, right? All the n samples, if you have collected all these things has been done within 1 second, then yes. But often the data that you have collected could be for, let's say, 57 seconds, right? In that case, you have to do some kind of processing on the data, or you have to do some manipulation of this particular value k. It has to be scaled and multiplied and so on. That will come to it like quickly, right? But it's just remember that it's not always k hertz, right? It's the kth frequency component. Okay, so you have a first frequency component, second frequency component, like that you'll have n minus 1, or basically total of n frequency components. And in assigning or knowing the exact value of the kth frequency component, you need to know what is the sample rate of the signal to start with. If you do not know the sample rate, you will never be able to tell what was the frequency, right? Because sample rate inherently gives you a relationship between how many samples were collected per unit time. Okay, so if you don't know the sample rate, you can always know the relative frequencies, right? Whether some frequency was more than the other, or what was the pattern of the different frequencies, whether you had a mix of 5 frequencies or you had a mix of 2 frequencies. These kind of things you can answer, but you cannot quantify that, oh, 7.2 hertz was present. For that, you need to know the sample rate. Okay, hope this is clear. And for the sample rate, just to mention, and most of the sensors, when you look at their specifications, they will mention a certain sample rate, right? The hardware will try to give you samples that are spaced uniformly in time, and you will see this this sensor supports 100 hertz, right? So we'll per 1 second, right? And they will be, the hardware will do a best job to put them uniformly spaced in time. Okay, and that's how all the intricacies about the ADCs and so on will come into play, how fast they can operate and so on. Okay. Okay, so now I'll do one more synthetic test where instead of having a 5 hertz signal, now I have 3 signals that are merged together. So the entire thing will look something like this, right? Which is not so neat. That was being shown to you earlier. I was showing an example of this 5 hertz sine wave. Now instead of just 5, you have 2, you have 5, and you have 7. And we are going to throw this particular thing inside the coiling machine and see how things work. Okay, so let's follow this, right? And on the x-axis, on the right hand side, I'm following the average weight. Okay, so I tried it till 10, but this gives you a pretty decent idea, right? So what I have plotted is the different frequency components, right? And for every component, I'm also looking at the weight, right? And I have already showed you how we are calculating the weight. We are just calculating the weight simply based on the center of mass, right, of the different sample points. So with this, I would be very easy for me to explain So you have basically samples here, right? All of them has some coordinate, and this goes back to your high school physics, right, where you tried to find out all this moment of inertia and so on, right? In that case, you actually had to deal with all these things. So you have this mass that is distributed in this fashion, and all you are interested in is figuring out what is the center of mass of the system. Okay, that's all we are doing, and that is the weight that is something that we are plotting. Okay, and for every value of the coiling frequency, we are repeating the entire exercise. So if it is 0.9, we do this entire layout, we find out the value of the weight, plot it. Okay, then we go to another value, let's say 1.1, right? In 1.1, the configuration changes. This is no longer the configuration, so you have a different distribution of the sample points. So now your center of mass will be at a different location. Okay, so it will shift somewhere, and now that is something that I have plotted. Okay, so since 2 was present, ideally once we approach 2, the components that are related with 2 is going to stack up, right? So because 7 and 5 was also present here, so it is sort of difficult, right, to exactly make sense out of it. But what we are trying to do here is a relative comparison. So 2 will get some kind of a weight W2.0, and that is something we are plotting here. Right? Note that this is a relative scale. So it now earlier, so this point was assigned to something which was much lesser in value. So the y-axis is scaled according to the value that is present. Right. Similarly, once we go to 5, it starts coming up, right? When we go to 5, it's pretty much just on one side, right? If you find out for this entire configuration, you can find out this weight. Okay, so this sort of gives you an idea to figure out the dominant frequencies, right? 2, 5, and 7. And similarly for 7, you will see the same phenomenon that is happening. So for 7 also, we can see that this is again stacked up in one particular direction, right? And the center of mass of the average weight is plotted here. Okay, so at least if you find out the maxima components, right, what are the 3 main peaks, you can always get through these values. Okay, so one is at 2, the other one is at 5, and the other one is at 7. Okay, so this is also working. The coiling machine, that intuition that I have given you, should also work if you have a mix of frequencies, right? It's not just for 1 hertz sine wave that I have shown, or a 5 hertz sine wave that I have shown in the very beginning, but also if you have a mix of frequencies, it is fine. We can figure out using the same formulation, using the same ideas, we can extract or segregate multiple frequencies. Okay, so what should be the complexity of this, right? The way we have done, like computational complexity, if you have n samples, let's say, and you are basically extracting n frequency components out of it, I want to know, based on whatever I have shown you, the computational complexity of this algorithm. Anybody? Hello?
Order of 1, sir.
Sorry? Order of?
1.
Order of 1? How?
Yes, sir, we are continuously plotting. So
no, forget plotting. Like, let's say this plotting is just for you to see all these things, right? Suppose you write a function f, right, and you are taking into input an array, right? That
Yes,
array
sir.
is of size n, right? And you do some stuff here and give me another array which is basically the weight. Right? This is the return. You are returning this weight array, right? I mean, weight matrix. So I'm trying to figure out the computational complexity of this entire algorithm?
Capital N into number of frequencies that we're taking.
Capital N into multiply. Yeah, exactly. So you are looking for every time. What are you doing? You are basically parsing that entire array, right? What exactly are you doing? Let's say you want to figure out whether the frequency 5 exists. What are you going to do? You are going to take up this part and this part, just wrap this entire set of data points, right? You have n data points here, right? You have n data points here. You are going to take all of these data points and put it around this garland you are going to make, right? So n will be the computational complexity given that you are searching for one frequency. If you are searching for, let's say, n frequency components, then it will be n multiplied by n square. Or if you are doing it for just k frequencies, it will be k multiplied by n. Okay. So this is very fundamental, right? This has nothing to do with even this class. So I am just repeating an operation over an array which is done k times. So k multiplied by n. Okay. Hope this gets on to hope you understand what I am talking about. Still, if you have confusion, please feel free to ask, right? Okay, so these are very fundamental things that we have to know, right, in this context, right? Okay, so now I'll show you that how the same concept can also be applied to real signals, right? Real, by real I mean data points that I have actually found out by doing sensing, right? I have shown you all the step counting in the first class, and then I have showed you the pulse oximeter example where I was extracting the IR sensors value of the red LED, right? The red LED was passing through the blood, and then the emerging out ray, we were looking at the photodiode voltage, right? If you remember, all of these are like real signals, and these are discrete signals, of course. And what we were trying to do is that finding out some sort of a periodicity that exists in this particular signals. Okay. So the frequency extractor doesn't change. We are still going to use the same code, and we are interested in figuring out what are the n components here. Okay. So let us. This is also some of the homework thing that you are doing, right? I am not asked you to implement it at all. So you are just going to use this Python API called DFT that is going to magically give you the plot on the right hand side, right? So I'm just asking you to like, you can, out of your own passion, you can try to implement this, right? Which is going to really be helpful in your career. Okay. So let's say I have this particular situation. I have this IR sensor data. I have taken 5 seconds duration of data that has been collected at 16 samples per second. So there are 80 samples I have. That's all. Okay. And I'm going to show you 40 frequency components, and I'm going to come to this later, right? Why 40, why not 80, why not 160, and so on. So there are something to do with Nyquist rate, right? That many of you know, but for complete coverage of the entire class, I'm going to explain that one more time. Okay, so for today, just assume that we are finding out 40 frequency components. Okay, so same business, just load the data, right? Now this is very sparse, so you can see the discontinuity in the this left hand side plot. Okay. Okay, so what happened now? So we are looking at all the frequency components. I just skipped 0 because 0, what does 0 mean? So there is absolutely no rotation. So what will happen is all the data points will be stacked up at 0 only, and you will see a very high value, right? That's why at 0th point, I have deliberately skipped that particular data point or the average weight, because it is just going to dwindle my entire plot, right? So I have skipped 0 hertz or 0th frequency component. Okay, and then looking at the other dominant peaks, you can see, okay, there is a fairly dominant peak here, right? And then this could be the other ones. Okay, and we are going to now increase, we are going to use the same data stream. So now instead of using a 5 seconds data, 5 second worth of data, we are now going to look at, let's say, 10 seconds worth of data. Okay, or even more. Let's look at the entire data set, right? I have collected, I think, 32 seconds worth of data, right? So you might not have the flexibility to wait for this 32 seconds and then give the data set to the system, often these systems are built at real time, right? So it has to operate on streaming data. So in that case, you have to continuously run this operation on a queue, right? You have a sliding window or a queue, and you have to continuously evaluate this entire spectrum or the frequency components on top of the queue, right? So in this case, I'm just giving you a demonstration, right? Suppose you are just trying to figure out the same frequency components in the signal, and you already know that the system is stationary in terms of that the frequency components doesn't change, right? It's just that it's going to give you endless amount of data, the amount of like whatever you ask for. So initially you were doing the analysis based on 5 seconds. Now you are doing the analysis based on 32 seconds worth of data. And now we'll see the same thing happening, right? Now I'm going by component, and because that we are having 512 samples, we are showing 256 frequency components. Okay, so see, sometimes the patterns become very, very distinct. It is a lot of fun if you actually try this out, and this is going to clear all your confusion regarding the like a frequency domain analysis, right? The basics of it, right? How magically do you get frequency components, right? Okay, so in this case, right, you will see whatever we had in the last class, in the last slide, right? It's pretty much the same, right? You have this component, you have another component here, and then you have another component here. You can ignore this one. This is very close to 0, right? And that is the reason we are getting this, right? Because now I have really stripped down the number of frequency components, right? Earlier we had something around 40, right? So this peak was missed out, right? Whereas now this has become much more granular, right? And that is the reason we are having this high peak on the left hand side. But whatever be the reason, this did not change, right? You still have these 3 sort of peaks spread across. Okay, so what is the difference in between these two? What difference did it make? So if you had 32 seconds worth of data versus 5 seconds worth of data, why do 32 seconds? Right? Any difference that you see? Okay. I'll basically anyway point you to the actual answer, right? So I have a series of these things done, right? Starting with 5 seconds worth of data and then moving towards 32 seconds. If you see the kind of prominence that you have for these peaks becomes much better, right? This could be something that is spurious, right? Or this is something that is not something that you are looking for, and the distinction becomes more and more better if you are digesting more number of samples into the system. Okay, so what we call this particular thing is related to signal to noise ratio, or SNR, where the signal that you are interested in is the weight of the actual peak, right? This is the actual peak of the signal that you are interested in, whereas we have a concept of noise floor, which is basically the randomness in the system that is always present, right? So you will always have a series of noise that comes along with your signal, and once you do this frequency domain analysis as well, that will have contributions in all the frequency components, right? That noise will be sort of spread across in all of the frequencies, right? So what happens is your noise floor, right? Whatever we call this as the average weight of the, let's say, noise floor, right? And this is your weight of the signal. So this ratio, right, the weight of the signal divided by the weight of the noise floor, that becomes better and better, right? And you have better resolution, right? You can actually have more, like, less spacing, right? This becomes more granular, right? So we will actually know what are the different frequency values soon, right? In maybe in the next class, but this gives you a clear benefit. That is something that you can understand till now. Okay, so how much in terms of frequencies you can go doesn't change, but what you can see is that better, more the number of samples, you are getting a better resolution, and you can actually achieve a better SNR. You can move around, you can actually move the noise apart and get your signal, right? And the prominence or the data extraction quality becomes much better, right? With more confidence, you can say that yes, this particular frequency is present, and you cannot have that much confidence if you are dealing with the 5-second data, right? This is not that separated out from the noise, right? As you can see, the noise floor is around 1 or 0.8, and your peak is at 1.4, whereas it is, the noise floor is still at 1, whereas your signal is present at 7, right? So this definitely gives a bump up in the clarity. Okay, so I'll stop here. Okay, any questions till here?
Sir, the frequency component, if we see that even the x-axis is getting scaled, even though structurally it remains the same. So now in the real domain, what frequency should I consider as the?
I'll cover, actually I had it today, but I have to talk more about the sampling rate and so on. So I'll cover in the next class. I mean, what you are asking is, like, let me again go back. So what you are asking is that how do we map it, right? How do you map 100 to a physical value of frequency, right? Whether it is
sir.
like 6.7 hertz or what, right? That's what you are asking.
Yes, sir.
Right, just I'll give you a short answer for today, right? It basically depends on the sample rate, because if you are doing at 16 samples per second, let's say, right, what will be the maximum value of your frequency that you can track? 8 hertz, right?
Yes, sir.
Okay, so that is uniformly scaled across the component. So I think you can take it, this one as, let's say, 0, and this is some kind of an F max, right? And if you know 0 and F max, you can do a simple unitary method to find out what does this mean, right? So 150 minus 0, right? So this corresponds to certain spawn of frequencies, and then you can look at what does 100 mean. Simple, and you can do the calculation, right? So F max doesn't change. It is impossible to change F max without changing the sample rate. Whether it is 5-second data or it is 5 hours data, doesn't matter. Okay, so all you are contributing to the system is making the SNR better. That's all. More data you are ingesting, your SNR becomes better and better and better. Okay, we will cover some of these things in the next class, and I'll keep it up to here, right? So that, like, we want to sync it up with other students also. Okay, so in the next class, I will not be present physically. So don't join the class per se. I will send you a recorded video, because I have to. I have some other departmental work that I have to anyway do as a part of a defense committee. So let me get through that, and then I'll share the video recording either on Saturday or Sunday. Right, in the weekend anyway, you'll be busy with the homework. So I'll share it as soon as possible. Okay, so thank you.